In tensor analysis, now we will see a very important tensor which is known as symmetric tensor. Actually, in the study of physics in different topics, you get several examples of symmetric tensors. In fact, the property of symmetry is an intrinsic property because you will see later on that the property of symmetry is independent of the choice of coordinate system. And so this symmetry property, or particularly this symmetric tensor, is very important concept of tensor analysis. So first of all, we will see what is this symmetric tensor, and then we will solve some of the important problems so that the concept of symmetric tensor will be completely clear to you. So let us start with to know what is this symmetric tensor first of all. And in this regard, I consider a second order, or you can say a tensor of rank 2, which is a covariant tensor. Let us consider that this A sub PQ, you know, this is the symbol which represents a covariant tensor of rank 2. And this symmetry property is actually defined for two indices. So definitely symmetric tensor, whenever you will define the symmetric tensor, at least the rank of the tensor must be 2. It means the tensor of 0 rank, that is a scalar, or the tensor of rank 1, that is the vectors, cannot be actually symmetric tensor. So for symmetric tensor, the rank of the tensor must be at least 2. So in the beginning, we consider a covariant tensor of rank 2, and this has been written by the symbol A sub PQ. This tensor Apq is called a symmetric tensor. But when it will call a symmetric tensor, the condition is that A sub PQ is equal to A sub QP. It means if you just interchange the indices, then the components of the tensor remains invariant. They do not change. So if this condition will be satisfied, then you can say that this covariant tensor of rank 2 Apq is a symmetric tensor. As I have told you that we find the proper example of symmetric tensor during the study of physics in different topics. So I have mentioned here two important examples. Definitely you have studied these tensors. You know, when we study actually the electrostatics, or you can say the electrodynamics, we study a very important second order covariant tensor, and that second order covariant tensor is known as quadrupole moment tensor. In case of multiple expansion of potential, you have studied this tensor in electrostatics. We denote this tensor by the symbol Qij, Q sub ij, you can say. In fact, this quadrupole moment tensor Qij is a symmetric tensor. And you know, if it is symmetric, what does it mean? It means this Q sub ij will be equal to Q sub ji. Similarly, in the study of electrodynamics, we study a very important second order covariant tensor, and that is known as Maxwell stress tensor. I hope you have studied. If you have not studied it, you can watch my video on electrodynamics, and you will find there the complete description of this Maxwell stress tensor. In fact, this Maxwell stress tensor is denoted by the symbol Tij, and it is also a symmetric tensor. And so you can say that this Tij is equal to Tji. So I hope you have understand the definition of the symmetric tensor, which is actually a covariant tensor of rank 2. In fact, in similar manner, we also define the symmetric property of a contravariant tensor of rank 2. The concept is not different, it is a completely same. So if you consider a contravariant tensor of rank 2, which is A PQ, or you can say A super PQ. These PQ are super indices, so we read it A super PQ. This tensor A super PQ is called a symmetric tensor, but only when we will interchange again the indices P and Q and the components will not change. So if A super PQ is equal to A super QP, then you can say that this contravariant tensor of rank 2 A super PQ is a symmetric tensor. So you can see that the concept of symmetry for a contravariant tensor and a covariant tensor are not different, but actually both are same. But these definitions are only for the tensor of second rank, which may be a covariant tensor or a contravariant tensor. But it does not mean that we define the symmetric tensor only in case of tensor of rank 2. In fact, we can define the symmetric tensor in case of all those tensors which have a rank which is either equal or greater than 2. And the tensor may be a mixed tensor. So to know the general definition of a symmetric tensor, let us consider that a proper example. We consider a mixed tensor, let us say A super LMN sub PQR. Here you know LMN are super indices or contravariant indices, and PQR are actually the sub indices, or you can say these are subscripts or the covariant indices. When you want to define the symmetry property in a tensor like this, which is a mixed tensor of rank 6 here, but this may be of any rank, then one thing you should mark here. We always define the symmetry with respect to the similar indices. It means if you want to define the symmetry of this tensor, you have to select the two contravariant indices or two covariant indices. It means you cannot select one contravariant index and another covariant index. You cannot select. So for this tensor, let us consider that we consider the two indices M and N. It means the second and third contravariant index we consider. So this tensor A, L, M, N, P, Q, R will be called a symmetric tensor with respect to the second and third contravariant indices M and N only when this condition will be satisfied. It means we will interchange M and N, but the result remains same. So if you A super LMN sub PQR is equal to A super LNM, mark here, Mn has been replaced by Nm, then you can say that this tensor A is a symmetric tensor with respect to the contravariant indices M and N. Mark this. In such cases, we always define symmetry with respect to a pair of indices, and that pair of indices must be in fact similar. Similar means those two indices should be either contravariant indices or covariant indices. Here we have defined the symmetry with respect to the second and third contravariant indices. So this tensor A is called a symmetric tensor with respect to the contravariant indices m and n only when A, L, M, N, P, Q, R is equal to A, L, N, M, mark this, N, M, P, Q, R. In fact, this tensor, if you want to define the symmetry of this tensor A with respect to a pair of covariant indices, let us consider we have to define the symmetry of this tensor with the covariant indices P and Q. You may select it. So this tensor A will be called a symmetric tensor with the covariant with respect to the covariant indices P and Q when this condition will be satisfied. You can see I have simply interchanged the indices P and Q to Q and P, and if these components remain same, then we say that this given tensor A, L, M, N, P, Q, R is a symmetric tensor with respect to the covariant indices P and Q. So this is the definition of symmetric tensor, and I hope you have understand clearly this definition. Have you understand or not? Can you definitely? I hope you have understand, because this is a very simple concept. Now in this regard we will see a very important theorem. This theorem actually defines that the symmetry property does not change by the tensor law of transformation. In other words, you can say that if a tensor is symmetric with respect to two similar indices in a coordinate system, let us say xi, it means unprimed coordinate system where I is 1, 2, 3, so on n. It means you are considering that your space is n-dimensional. So if we consider a symmetric tensor in a coordinate system, let us say xi, or a coordinate system S with variables xi, then this tensor remains symmetric with respect to the two indices in another coordinate system S prime 2. And another coordinate system, you say that in this another coordinate system the variables are x prime I. It means due to change in coordinate system, the symmetry property of a tensor is not affected. So we will explain this very important theorem by a proper example. You can consider a second order tensor that may be a contravariant tensor or a covariant tensor. For proof, you can consider anything. So let us consider. Let Apq. You can see I have considered here a second rank tensor which is covariant tensor. So Apq equal to a covariant tensor of rank 2 in a coordinate system xi in which it is symmetric. In fact, in this coordinate system, we consider that this tensor is a symmetric tensor. And if you say that this tensor is a symmetric tensor in the coordinate system xi, what does it mean? Definitely then we can write A sub PQ is equal to A sub QP. Sub QP. Let us say this is equation 1. Now consider that the components of this tensor in another coordinate system, let us say x prime I. So let A prime PQ equal to components of Apq in a coordinate system, let us say x prime I. So A prime sub PQ, these are components of this tensor Apq in the coordinate system with variables x prime I. Then according to this theorem, if this tensor Apq in coordinate system xi is symmetric, that is Apq is equal to Aqp, then according to the statement of the theorem, this tensor A prime PQ will be also symmetric with respect to the indices P and Q. Then we have to show that A prime PQ is also equal to A prime QP. This is the result actually which we have to prove. And when this result will be proved, you can easily say that this symmetry property is independent of the coordinate system, because if a tensor is symmetric in one coordinate system, then that tensor is also symmetric in another coordinate system. So let us see how this result can be proved. That is A prime PQ is equal to A prime QP. We try to prove it by the law of transformation of tensor. So now you can see, applying the law of transformation of tensor of second rank, which is covariant tensor, let us see what will be this A prime PQ. Let us consider that the components A prime PQ, which are actually components of a tensor in the prime coordinate system, and corresponding to these components, the component of that tensor in the unprimed coordinate system, let us say that is A sub ij. Let us consider. Then you know from the law of transformation of a covariant tensor of second rank that A prime PQ is equal to Aij and del xi by del x prime p. You can remember the transformation law for a covariant tensor of second rank, and times del xj by del x prime q. You know it. But as the statement of the theorem says, or you can see the equation number 1, that in unprimed coordinate system, this tensor is symmetric. It means Apq is equal to Aqp. So you can say that this Aij will be equal to Aji, because you know this Aij are actually the components of this tensor in the unprimed coordinate system, that is the coordinate system xi. So but you can say this A sub ij is equal to A sub ji as it is symmetric in coordinate system xi. It is just the statement of our theorem. And therefore, you can replace this aij by aji. Therefore, we should write A prime PQ is equal to A sub ji and times this much, you can see, times del xi by del x prime p times del xj by del x prime q. Now this is just a simple multiplication, so you can write it A sub ji del xj by del x prime q times del xi by del x prime p. Now see this, and remember the law of transformation of a covariant tensor of second rank. If that transformation law is in your mind, you can easily say that this is nothing, this is simply A prime QP. A prime QP. You can compare this from this result, that when there is Aij, then here is P and Q, and when there is Ji, then there is Q and P. So this is A prime QP. So finally, you can see we have obtained the result that A prime sub PQ is equal to A prime sub QP. And this is the result which was to prove. It means now it is clear that if a tensor, here actually I have taken the example of a covariant tensor of second rank, but it is not necessary to take this example. You may take a tensor like this, A super PQ, you may take it, and then you can prove that if A super PQ is equal to A super QP, then you can prove that this A prime super PQ is equal to A prime super QP. And in similar manner, you can also prove that if, let us say, ALMN PQR is equal to ALNM PQR, then you can prove in the similar manner that this A prime LMN PQR will be equal to A prime LNM PQR. You can prove this. So this is just a theorem, so I have taken the simplest example of a covariant tensor of second rank and proved the theorem. So in this way you can say that the property of symmetry is independent of the choice of coordinate system, that may be a unprime coordinate system or the prime coordinate system, but a tensor which is symmetric in one coordinate system, that will be definitely symmetric in another coordinate system. But remember, that will be not valid in case of a mixed tensor of second rank. When we will study the antisymmetric tensor, then you will find such a concept. So here the indices with respect to which we define the symmetry is either the covariant indices or contravariant indices. In that condition, you can say that a tensor which is symmetric in one coordinate system remains symmetric in all other coordinate system. And that's why we say that the property of symmetry is independent of the choice of coordinate system, and that is why we say that this symmetry property is an intrinsic property of the tensor. So now this theorem is completely proved. Now let us see an important problem related to this symmetric tensor. So first of all, I will write here that problem and then we will solve it. In fact, the problem says that a symmetric tensor of rank 2, remember, a symmetric tensor of rank 2 has at most n into n plus 1 divided by two different components in n-dimensional space, and we have to prove this. So that a symmetric tensor of rank 2 symmetric tensor of rank 2 has at most n times n plus 1 over 2 distinct, or you can say different, distinct components in n-dimensional space. N-dimensional space. See this problem. Here two things is to mark. First of all, the tensor is symmetric and it is not any tensor, but mark this. This is just a tensor of rank 2. So this result which we have to prove, it will be valid only when the tensor is of second rank, not for other rank of tensor. So if your tensor is of second rank, but that second rank tensor may be either a covariant tensor or a contravariant tensor, but if that is of second rank and is symmetric, in fact in that condition you can say that the total number of independent or distinct or different components of such a tensor is n into n plus 1 over 2. So let us solve this problem. So after solution you will get this idea that how we can find the total number of independent components. And once you know the total number of independent components, you can also find the total number of dependent components. And This problem is very important for solving the numerical problems, particularly objective type problem in the different examinations. So you can see here, as we have to consider a symmetric tensor, so it is just our choice. We can consider a covariant tensor or a contravariant tensor. You can select it. So let us say that we select or we consider a covariant tensor of rank 2. So let Apq be a tensor of rank 2, and you can see this is a covariant tensor. But as I have told you, you may also take a contravariant tensor of rank 2 at the place of this A sub PQ. And we also consider that the space is n-dimensional, and you know, in n-dimensional space, the total number of components, not independent, total number of components of a second rank tensor in case of n-dimensional space, you have seen earlier in the definition, that number is actually equal to n square. So if Apq be a tensor of rank 2, then total number of components of this tensor is n square in n-dimensional space. N-dimensional space. And you know, if you want to write those in components of Apq in the form of matrix, you may write like this. This Apq is equal to matrix A11, A12, so on, A1n. Again, A21, A22, so on, A2n. And similarly, A n1, A n2, n2, and A nn. These are actually the n square couple. You can see that this matrix is actually a square matrix, n by n matrix, and so the total number of elements or components of this matrix is n square. You can see the number of components in a row is n, and the number of components in a column is also n. So the total number of components of this tensor is n square. Now see the components on the diagonal or diagonal components. The diagonal components, you can see these are A11, A22, A33, and similarly ANN. Actually, these are the n independent components. It means these indices never repeated. So there are n independent components, and those components are A11, A22, A33, and so on. That is, you can say that the diagonal components, the diagonal components A11, A22, so on, ANN, NN are independent components. And what is its number? You can see this is from 1 to n. It means the total number of independent components, that is the diagonal components, is n. So the number of independent components this is equal to n. Now see the off-diagonal components. Off-diagonal components are A12, A13, so on, and in where the two indices are different. So the off-diagonal components of diagonal components are A12, A23, so on, A32, and so on, in this way. It means these are the components corresponding to distinct subscripts. That is, the two indices or subscripts are not equal, but they are different. So, as the total number of components you know is n square, and the number of independent components here, that is the number of components which are on the diagonal of this matrix, that is actually equal to n. So the total number of off-diagonal components will be n square minus n. Therefore, the number of diagonal components what will be that? Since total number of components is n square and number of components on the diagonal, that is n, so the total number of off-diagonal components is n square minus n. But as you know, in case of off-diagonal component, the two indices are unequal, not same. But our tensor is symmetric. So when you will interchange the subscript in for any component, the value will remain same. That is not different because the tensor is symmetric. As the tensor is symmetric. So, you know, then A12 will be equal to A21. Similarly, A23 will be equal to A32, and so on. It means the total number of independent off diagonal components will be just half of this number, just half, because this is total number of off diagonal components. But in case of off diagonal components, due to the symmetry property of this tensor, when we will interchange the subscript, the component remains same. So A12 and A21 both represent the same component, and that's why we will count these A12 and A21 1, not 2. So in this condition, you can say the total number of independent components, or total number of off diagonal independent component, this will be just half of the total number of diagonal components. So therefore, number of independent of diagonal components, this will be just half of that value, n square minus n over 2. Now see here, the total number of independent components which are off diagonal elements is n square minus n by 2, and the number of components lying on the diagonal of this matrix is n. So now you can say the total number of independent components, or different components, or distinct components will be sum of these two numbers. So now the total number of different, or you can say distinct, independent components. What will be this? If you consider that this number is equal to a small n, then this small n will be equal to n plus n square minus n over 2. And this is equal to what? This will be 2n plus n square minus n over 2, and this is n square plus n over 2. Now if you will take the n as a common factor, then this is small n, which represents actually the total number of different independent components of this second order tensor in n-dimensional space. So this n is equal to n times n plus 1 over 2. And this is the result which we have to prove in this problem, you can see. Now, if you take a proper example, let us say that our space is 3-dimensional, Euclidean space. It means n will be 3. And rank of the tensor is fixed. The rank is actually 2. Remember, this result is only for the tensor of second rank, not of higher rank or lower rank. So n is equal to 3. It means you are considering that your space is three-dimensional Euclidean space. So in three-dimensional Euclidean space, if there be a tensor, there will be a second order symmetric tensor, then the total number of independent different components of this tensor will be what? See here. Here we will replace this capital N by 3. So this will be 3 into 3 plus 1 over 2. And what will be this? This will be 6. This will be 6. And so the total number of independent components, independent and different components you can say, of a second order symmetric tensor in three-dimensional space is equal to 6. And as I have told you earlier that these tensors, that is the quadrupole moment tensor and the Maxwell stress tensor, actually in 3D space, this quadrupole moment tensor has 6 independent components, and this Maxwell stress tensor has also 6 independent components. So this is just the idea of the symmetric tensor, and I hope after these examples the concept of this symmetric tensor is definitely clear to you, and so I hope you will be very happy to know that in the next lecture on this tensor analysis we will see the concept of SQ symmetric tensor or anti-symmetric tensor.